Okay, in today's video, we're going to do, this is the part B that I mentioned the other day. So we focused on exponential equations and how to use logarithms to undo and solve them. And then today we're going to go over the logarithmic equations and show you how to use exponents to undo and solve them. So we're going to advance to example, I think it's example 13. Actually, we're going to start on this slide, solving log equations. And so again, there's a whole list of stuff. Let me just kind of look it over real quick. If there's only one log, put the equation in exponential form and solve. If there's one ln, convert it to log base e, then put it in exponential form. If you have one log on either side of the equal sign, use the one-to-one property. And if you have multiple logs, condense and then use the one-to-one property or change to exponential form. So that's a lot of good tips. However, until you see the problems, you're not going to understand what all of this is, okay? The only thing I do want to focus on that we haven't discussed before is that log expressions can only be used for positive real numbers. So you're going to have a log of a number, right? This number has to be positive. This value, okay, has to be positive. So in other words, it cannot be negative and it cannot be zero. So if you get a value for x and x happens to make this number negative or zero, then it's an extraneous solution and you have to cancel it, okay? So I'll show you. There's a few examples of those in the problems. So I'm coming back to this slide after having done all of the examples just to show you that now we've kind of done all of these. The first one says if you only have one log, you put the equation in exponential form and solve. If you have one natural log, convert it to log base e and then put it in exponential form. If you have one log on either side of the equal sign, use a one-to-one property to solve. And if you have multiple logs, condense and then use the one-to-one property. So again, these are all the things we did. We had every one of these examples here. And once we kind of go through all the problems, you're going to see that we tackled all of them. And again, the most important thing is if it starts out as a logarithmic function, when you insert those bases and you get your x's, you need to check and make sure that none of those x's create a log that has a 0 or a negative, because then it's extraneous and that answer doesn't count. So we're going to start with our very first problem. We're going to do the natural log of x equals 3. So let's first write that as log base e of x equals 3. And so the reason we can't solve this log, we can't type it into our calculator because we don't have an x value here. X is there and we have to kind of get rid of that, right? So what we're going to do is we're going to come over to here and we're going to turn this into an exponent. We're going to do a base of e raised to the log e to the x power, and we're going to do the same thing over here. We're going to do e raised to the third power. What happens is, remember that when you have this base raised to a log with the same base, they cancel. And what that does is it gets the x out of that spot. So x equals e to the third power, and when I type e to the third power into my calculator, it's approximately equal to 20.086. And again, if I plug this value into here, I sort of check it. Is it positive? Yes, it is. So it's a valid answer. So you're going to have to check your answers on these to make sure that it never makes whatever the log is of, right, that it never makes it negative or 0. So now we come to the next problem, and it's very similar to that last problem. You've got log base e of x equals 2. And so I know that if I just do e to this exponent, then the other side is also e to the 2 exponent. And so the e and the log base e will cancel, and it'll leave me with x equals e to the second power, which means x is approximately equal to 7.389. And again, since this is a positive number, I know this is going to be positive, and therefore it's a valid solution. Okay, I go to 15 below, and this is something we learned in our last section on properties of logs, and we learned that if I have log base 3 on the left and a log base 3 on the right, those can cancel out, and I can be left with 5x minus 1 equals x plus 7. And now it's just an algebra problem. I'm going to solve for x. I'm going to subtract x from both sides. 4x minus 1 is 7. I'll add 1 to both sides. 4x equals 8. And when I divide both sides by 4, I'll get that x equals 2. And again, if I plug 2 in here and I plug 2 in here, both of those end up being positive, and so this is a valid solution. And when I get to this last one, I notice this one's finally one that's a little bit different, right? Because this one I have 2 logs on the left and 1 log on the right. And so what I'm going to want to do here is I'm going to want to condense these to 1 log, okay? Because they have the same base, they're both base 6, and because it's a subtraction, I know this can be written or condensed as log base 6 of 3x plus 14 over 5. And that will equal log base 6 of 2x, okay? And so this is fully condensed on the left, fully condensed on the right, and now because I have a log base 6, I can free up the variable by doing 6 to this power, okay? And I'll do 6 to this power on the other side. What that's going to free me up to do, well, I actually don't even need to do that, actually, because since they're both log base 6 of it, I can do what I did in the last problem, and since they're the same log with the base, I can just cancel that out. So I don't even need to raise it to that power, okay? So again here, I'm going to be left with 3x plus 14 over 5, and it's going to equal 2x. At this point, I'm just going to do algebra. Oops. I'm going to multiply both sides by 5. It's going to cancel. I'm going to get 3x plus 14 equals 10x. I'll subtract 3x from both sides. So I'll get 7x, and then I divide both sides by 7. And so I'm going to get x equals 2. Okay? And then again, I think about plugging 2 into here and 2 into here, and I realize that if I do that, or when I do that, they're going to be positive numbers in those parentheses, and so 2 is a valid solution. So in this slide, we've kind of tackled a couple of scenarios. If I go back to the list on the page before, you're going to see a couple of these scenarios were there. At the end, I'll kind of go through it with you. So now we're going to get to some problems. Again, these are a little bit more complex, but again, a little bit repetitive still. Log base 2, it cancels. I'm left with 2x minus 3 equals x plus 4. And now I just do algebra. So I subtract x from both sides. I get x minus 3 equals 4, and then I add 3 to both sides. X is 7. I do a quick check. It's valid. It's a valid solution. When I get to number 18, again, I notice that I have 2 logs on, they're all log base 10, right? When you don't see the number, it's log base 10. I see that I have 2 logs on the left, so I'm going to work on condensing these. This is going to be, because it's a subtraction, I know that I'm going to do log base 10 of 4x over 12 plus x, and that's going to equal log base 10 of 2. Now that my logs are the same, I can cancel them out, and I can just have it as a basic algebra problem. 4x over 12 plus x equals 2. I'll multiply both sides by 12 plus x. These are going to cancel. I'm going to get 4x equals 24 plus 2x. I'll subtract 2x from both sides, and I'm going to get 2x equals 24, which means x is 12. And when I come over here and I insert 12 there and there, both of those end up being positive, which means this is a valid solution. Now when I come to this one, again, remember that your goal is always to get the log and the variable by itself. So when I come to this problem, I'm going to start it by moving the 5 over to the other side by subtracting 5 from both sides. So I'm going to get 2 times ln of x equals -1, okay? And then I'm going to divide both sides by 2. I'm going to get ln of x equals -1/2. And now I know that ln of x is log base e of x equals negative a half. And so again, in this problem, I know that if I just do an e here and make this an exponent, I can do it to the other side. So it's going to be e to the log e of x power, which means this is going to cancel, and it's going to leave me with just x. So x equals e to the negative 1/2 power. And when I type that in my calculator, I'm going to get approximately 0.607. Again, this is a positive number, so when I insert that there, that's going to be positive, and therefore this is valid. So far we haven't seen the ones that are extraneous, but I promise you, or I assure you we will. I'm going to come over to here. Let me just kind of move this over. 2x equals 24, x equals 12. Okay, and I'm going to just kind of make a little bit of room here for this problem. So again, this one's similar to 19. Again, I want to isolate the ln of x, and so what I'm going to have to do is subtract 7 from both sides. So 5 minus 7 is minus 2. Then I'm going to divide both sides by 3, and I'm going to get ln of x equals negative 2/3. At this point, I'm going to write ln as log base e of x equals negative 2/3. And I only really do it so you can see it. But you can see that I have to kind of put this e here and make that an exponent. So again, I do it to the other side. That's going to cancel the e and the log e, and it's going to leave me with x equals e to the negative 2/3 power, which when you type that into your calculator is approximately 0.513. Okay, and again, since that's a positive number, when I insert it into the x, it's going to be positive, and it's a valid solution. So I'm checking every time when it comes to solving logs, and you should do that, okay? Now, when we get to this slide, this is where we really start getting to a little bit more intricate problems. Right here, for example, we want to isolate the log of base 5 of 3x, which means I'm going to have to divide both sides by 2. I want to get rid of that 2. So I'm going to do log base 5 of 3x equals 2. And then again, I want to free up the 3x, and I can only do that by making it an exponent. So I'm going to do 5 to the log base 5 of 3x power and 5 to the second power. This side's going to cancel, and I'm going to be left with 3x equals 5 squared, which is 25. So x equals 25 over 3. Or if I want to do it as a decimal, it's going to be approximately equal to 8.333. And so this is my solution. And again, if I plug that positive number in here, it's going to be positive, and so it's valid. Okay. Now there are a couple of things that some of you might have noticed, like in this problem, I could have done some things I learned before. Like, for example, I could have moved the 2 over to here. Right? And so it could have been log base 5 of 3x squared equals 4. I get that. I could have also, at that point, inserted the 5 and inserted the 5 here. So it would be 3x squared, 3x, the whole thing squared, and it equals 5 to the 4th power, which is 625. At that point, right, I could have squared 3x. It would have been 9x squared equals 625. I would have divided both sides by 9. I would have gotten x squared equals 625 divided by 9, and I would have taken the square root, and I would have gotten positive and negative 25/3. And I would have seen that negative 25/3 would have been extraneous, and so the only valid answer would have been positive 25 over 3. So I would have gotten the same answer, but I would have dealt with bigger numbers, and I would have had to check for extraneous. And so yes, you can do it that way, but I wouldn't bother moving this to the exponent spot. I would just divide it out when possible. But yes, for those of you that kind of were seeing that and wondering if that was something you could do, yes, you could. Okay, any of the rules you've learned, you can apply here. Okay, I'm just kind of showing you the most efficient way to solve these. Again, for 22, same idea. Yes, I could, move this 3 here, but it's going to give me numbers that are bigger than what I want. So what I'd rather do is divide out the 3. It's just easier. So I'm going to be left with log base 4 of 6x equals 9 over 3 or 3. And then I'm going to do 4 to this exponent, right? And 4 to the 3rd power. Again, reason I did 4 was to free up the 6x. I got rid of the log base 4, and now I've got 6x equals 4 to the third power is 64. So divide by 6, and I'm going to get x equals 64 divided by 6. And again, when I do that, I'm going to get, again, I could simplify that, right? It would be 32 over 3. But either way, it's approximately equal to 10.667. And since that's a positive number, I know when I plug it in there, it's going to be valid. All right, so we keep going. So now we look, and now we're seeing the pattern, right? We look here and we see, okay, the left side has 2 logs. So what I'm going to want to do is I'm going to want to condense them. So I'm going to want to condense these. Because I'm adding here, I know that that's multiplication. So that's going to be log of 5x times x minus 1 equals 2. I can distribute that 5x. I'm going to have to do it sooner or later. So I might as well just do it and get it over with. And now I realize, I have a log base 10 here. So I want to free up the 5x squared and the 5x. So what I'm going to have to do is create a base of 10 and make this an exponent. And I'll do the same thing to the other side. So now this cancels, and I'm going to get 5x squared minus 5x equals 10 squared, which is 100. And now for the first time, we're solving with an x squared. It's a quadratic, and so we have to use our skills to solve quadratics. We know that to solve a quadratic, you move everything over to one side, and you make the whole thing equal to 0. You know that whenever possible, you factor out a GCF, which in this case is 5, equals 0. And you know that when you factor, you've got to have two, binomial here. It's going to be x minus 5 and x plus 4. So I look for my factors that have a variable in it. I only have 2 factors with a variable, and I set those factors equal to 0. So x is 5, and x plus 4 equals 0, so x equals negative 4. Now I have to check, especially when there's an x squared, okay? But I definitely have to check here. So if I take the 5 and I plug it into here, this is going to be positive, and this one's going to be positive. So the 5 is a valid answer, okay? So 5 is good. Negative 4, if I type negative 4 in here, I get negative 20. That's no good. So 4 is extraneous. I can't have it. So there's only one solution here, and the one solution is x equals 5. Okay, so again, remember to check. This one required checking. When I go to number 24, again, I see that I have 2 logs on the left, so I'm going to, again, condense my logs. Because of the addition, I know that this is log base 10, right, of x times x minus 9 equals 1. I can distribute that if I want to. So let me do that. So log base 10 of x squared minus 9x equals 1. And again, now I want to get rid of the log part of this completely, because again, my goal is to get to free up the x, because I'm trying to solve for x, and I can't solve for it when it's wrapped up with the log. So now I've got this, so what I'm going to do is, again, I'm solving a quadratic, so I'm going to bring the 10 over. I'm going to factor x minus 10, x plus 1 equals 0. So x is 10, and x is negative 1. And again, I check. So I come over to my problem here, and I say, okay, if I plug 10 in, this is positive, this is good, and 10 minus 9 is 1, which is also positive, so 10 is fine. So 10 is a valid solution, so I know I can keep it. And then negative 1. Well, the log of negative 1, that's negative, can't have it, so this is out. And so this is only, again, there's only one solution to this problem, and it's x equals 10. Now, 25 is kind of that's probably the toughest problem here. I'm going to rewrite it a little bit to give us some space. But 25 basically is log of x equals the square root of log x. Now, this is a challenging one, and I want you to pay attention to the little details here, because this is probably the most difficult problem that we're going to cover, okay? First thing you're going to do is you're going to set it up where you're going to take the log of x out of the square root. So you know that log of x, the square root of log of x, is the same as log of x to the 1/2 power, okay? So that's a pretty decent place to start, right? Now here you might be thinking, well, hey, I've got these common logs. Why can't I at this point do 10 to the log base 10 and do 10 here and just cancel? Well, I can't do that in this problem because this log of x to the 1/2 power is throwing it off for me, okay? There is a difference between the entire log of x being raised to the 1/2 power and just x being raised to the 1/2 power. If it was just x, yes, I could do 10, this is base 10, and it would cancel. But because the log is also being raised to the 1/2 power technically, or really it's not the log, it's like the whole thing, I can't do it. So I have to work with it as a unit. So I'm going to start by figuring out, well then how can I get rid of this 1/2 power on the right side? And one thing that I know I can do is I can raise the whole thing to the 2nd power. So I can square log of x over here too. Now this is where you need to be careful. On the right, this is easy because I'm going to do power to power, and I know that 1/2 times 2 is 1, so this just leaves me with log of x. Easy. On the other side, if I square log of x, okay, what is going to end up being squared is the log part of it. So this is kind of different. The squared part goes to the log, not to the x. So it's going to be log squared of x. And I know this is weird, but it is something that you're going to have to learn to do. So when the entire log itself is the log of something is squared, it's the log squared. Okay, so now I have log squared of x equals log of x. And this is kind of like when you have x squared equals x, okay? How you solve this is you have to bring the x over, set it equal to 0, factor out a GCF, and solve, okay? So that's what we have to do here. So I have to bring the log on the right over to the left. So log squared of x minus log of x equals 0. I'm going to factor out the GCF in these two terms, which is log of x. So this one's going to have log of x left over minus 1. And I know this is really weird. We have not really done this, okay? So now you have log of x equals 0, and you have log of x minus 1 equals 0. And we have to solve for that, okay? So now what I can do is I can now do 10. This base is 10. So I can say 10 to the log of 10 of x. That's going to cancel. That's going to leave me with x. And x equals 10 to the 0 power, which is 1. So here's one solution. On the other side, I have to isolate the log of x first. So I'm going to add the 1 to both sides. At this point, I'm going to do the 10 and make this an exponent, and I'm going to make this a 10 and that an exponent. When I do that, this is going to cancel, leaving me with x, and 10 to the 1 power is 10. So I got two solutions here, 10 and 1. And when I go to the original problem and I plug the 10 in, that's positive. When I plug the 1 in, that's positive. When I plug the 10 in here, or the 1, it's also positive. So I know these are both valid solutions. So there's two solutions here. And now on this last page, I don't think there's really anything on this last page that's as difficult as that last problem. So again, let's just kind of keep going. When I look here, I see that I have a log on the left and I have a log on the right, but I've also got this 3. And because I have the 3, or the plus 3, or the 3 plus, I can't just cancel the logs. So what I have to do is combine the logs together on one side and condense them. So it doesn't matter which side. I'm going to keep log 11x plus 9 on the left, and I'm going to subtract log x plus 4 from the right. So it's going to cancel from here and move over, and it just equals 3. Now that I have both logs on the same side, I'm going to condense them. So I'm going to have log, and because it's a subtraction, I know it's 11x plus 9 over x plus 4 equals 3. Okay, and so again, I know this is base 10, so what I'm going to do here is now I'm going to make it an exponent. And by doing that, I insert the base 10, make the rest exponents, and now I know this is going to cancel. So I'm going to have 11x plus 9 over x plus 4, and it's going to equal 10 to the 3rd power, which is 1,000. I'm going to multiply both sides by x plus 4 here. So it's going to cancel it here, and then it's going to be over here. So when I do the math, I'm going to get 11x plus 9 equals 1000x plus 4,000. Oh, I forgot. On this problem, by the way, I know that there was a typo, and they wanted us to change this problem. So I need you guys to kind of go back here and change this to a 3. I forgot about that. So this is, I'm just going to change the values here, okay? So this should have been a 3. This one here should have been a 3, right? When I multiplied that down there, should have been a 3. Okay, so, and again, and I'm multiplying by that. So here, instead of 4,000, I should get 3,000 because it should have been a 3. So it was a typo, and the reason we did it is we wanted to show you an extraneous answer, and I'll show you after. So when I move the 1,000 over to the left side, I'm going to get 989x equals, and then, or negative 989x equals, and over here when I subtract the 9, it's going to be 2,991. So x equals 2991 divided by negative 989, and I'm going to get approximately, for this answer, negative 3.024, I believe. And now when you see this negative and you go to plug it in, well, if I plug in negative 3 there, that's going to make that side a negative. And if I plug in a negative 3 here, negative 3.024, that's also going to make this one negative. And so this answer cannot happen, okay? It's extraneous, and because I have no other, this is a no solution, okay? So this number 26 has no solution, okay? When we go to 27, this is one we did yesterday. This isn't even a log question, so I'm surprised it's here. But basically, I have 6 to the x minus 3 power. I have 3 to the 4x plus 1 power. And for this one, I'm going to have to insert, like I did yesterday, I'm going to have to actually insert a log here. So I'm going to have to do ln of, well, let me just do it on the next slide. So I'm going to have to do ln of 6 to the x minus 3 power equals, and I'm going to do ln of 3 to the 4x plus 1 power. So these exponents here are now going to be moved to the front to start this problem. So I'm going to get x minus 3 times ln of 6 equals 4x plus 1 times ln of 3. I'm going to distribute the ln of 6, and I'm going to distribute the ln of 3. So I'm going to get x ln of 6 minus 3 ln of 6 equals 4x ln of 3 plus 1 ln of 3, which I don't really have to list the 1, right? So I want everything with x on the left, let's say, and I want everything without an x on the right. So my left side's going to be x ln of 6 minus 4x ln of 3, and that's going to equal ln of 3 plus 3 ln of 6. And again, now I'm going to factor out the x. I'm going to get ln of 6 minus 4 ln of 3 equals, and again, the left side stays the same. And I'm going to divide both sides by this here. So ln of 6 minus 4 ln of 3. So ln of 6 minus 4 ln of 3. And so I know that x is equal to whatever this is. Now, when I do that on my calculator, I know that it is approximately equal to negative 2.4874. And again, I would look up here, and I don't have to check this one because it's exponents. Okay, so exponents I don't have to check, only when I'm dealing with logarithmic functions. Now, there was a way I could have condensed a little bit on this problem. Again, on when I got to here, for example, I could condense that numerator. That numerator starts out as ln 3 plus ln of 6 cubed, right? Which then becomes ln 3 plus ln 2 think it's 216. And then I can also multiply those. So it could be ln of 648. So when I do all the math, this ends up being ln of 648 over, and then when I do the denominator is going to be ln of 6 minus ln of 3 to the 4th power, right? And then it's going to be ln of 6 over 3 to the 4th power, which is 81. And so this denominator would be ln of 6 over 81. And if I did the math for that, I'd get the same answer. So if you like the idea of condensing before you put all this, this whole expression into your calculator, that is fine as well. I think it leaves a little bit more room for error in the condensing part of it, but then I think it gives less room for error in the actual calculator part. So I guess it depends on what your strengths and what your weaknesses are. Okay, so anyway, but that's the answer for that one. And then we're going to do, let me see what number we're on now. Let me erase this one. Okay, so we're on the last two, I think. So let's go to this one. We've got, this one's kind of interesting because if I rewrite it as log base e of e to the x minus 2 times log base e of e equals log base e of e to the 4th power, I think you'll notice that every single one of these kind of meets the criteria of one of our properties, right? Because this one here, log base e of e, cancels and it's just x. This one here is 2 times log e of e, which is 1, and 2 times 1 is just 2. And then over here, this cancels and this is just 4. So this just ends up being x minus 2 is 4. And if I add 2 to both sides, I'm going to get x equals 6. And so that one kind of was weird. It didn't really have to use anything but the basic properties from the beginning. So sometimes we can sneak some easy ones in. And then this one, let's look at this one. Let's start by getting rid of the radical, log base 2, and then it's going to be 2 times x squared, and that's going to be all to the 1/2 power. So I exchange the radical for the 1/2 power. And over here, I just have 3/2. Okay? Now, the whole 2x squared to the 1/2 power, that is all within in the framework of a log. And so I'm going to do 2 to this power so I can free it up. And I'm going to do the same thing here, 2 to the 3/2 power. So this will cancel, and I'm going to have 2x squared raised to the 1/2 power equals 2 to the 3/2 power. Now here, before I even try to solve all this and work it out, what I'm going to do is I want to get rid of those fractional exponents, especially the one associated with the x. So what I'm going to do is I'm going to raise this whole thing to the 2nd power. And again, if I do it to the left, I have to do it to the right. So over here on the right, what I'm going to do is have a power to a power. So it's going to be 2x squared, but it's going to be 1/2 times 2 is just 1. So it's just 2x squared. And over here, I'm going to get 2, this 2 and this 2 will cancel because 3/2 times 2 is just 3. So it's going to be 2 to the 3rd power. Okay? So basically I've got 2x squared equals 2 to the 3rd power. So 2x squared equals 8. Divide by 2, divide by 2. I'm going to get x squared equals 4. And when I do the math, I'm going to get x equals the positive and negative square root of 4, which is positive and negative 2. And again, now I have to kind of ask myself, right, can I plug in both of those? Are they both valid? Well, if I plug 2 in here, I'm going to get 4, and 2 times 4 is 8, so I'm going to get the square root of 8. If I plug negative 2 in, I'm also going to get 4, and 4 times 2 is 8, so it's the square root of 8. So positive and negative 2, because the x is squared, it doesn't matter that it's negative, and both are valid. And so both solutions are valid there too. So these are all the problems, guys. We're going to go back real quick to the slide that talked about the different things you did, like the very first one.